In Chapter 7, we're dealing with equilibrium, and specifically to start out, we're talking about what dynamic equilibrium is. So, in general, we could have three possible things occurring when we put two or more things together. We could have a reaction that goes completely to the products. We could have a reaction that when we put things together, no products are actually formed. And we could have a reaction where both the reactants and the products are forming. And so these three instances, let's take a look at the first one. The products are energetically favorable when we have reactants going completely to products. That's because it has a low activation energy. And we've got an image from a titration there where the acid and base are reacting to form water and a salt, and we see that with the phenolphthalein. The second one, we have not forming products. Something that could theoretically happen, so it's energetically feasible, but the activation energy is too high without altering the reaction specifications, like adding an electrical charge, increasing the temperature, changing the pressure if we're dealing with gases. We've got some water as an image there because water can decompose into hydrogen and oxygen, but it's not energetically feasible to do so because of that high activation energy. So if I have water just sitting, I'm not forming a bunch of hydrogen and oxygen at all times. The third instance, forming the reactants and the products, the energy of the reactants are similar to the energy of the products, so they can go back and forth and back and forth. What I have there is a picture of some hydrogen chloride, hydrochloric acid in other words, with some ammonia, and they're reacting, and we see that white vapor in the bottleneck of the Erlenmeyer flask that's forming some ammonia chloride. But it's going back and forth. It's that nice cloudy haze that's going back and forth between ammonia plus hydrochloric acid and the ammonium chloride. So we have what's called a reversible reaction. The reaction does not go to completion, so we don't have that low activation energy. We've got the same energy in both directions. It's forming the reactants as well as the products. So once some products are formed, it goes back and forms some more of the reactants and vice versa. The symbol that we use is a forward arrow and a backward arrow. The general form, if I had a double displacement reaction, would be A plus B goes to C plus D. If the products are slightly more favorable in energy, we would write it with the top arrow as longer than the bottom arrow. And in the other direction, if the reactants are slightly more favorable, then we have the reverse reaction, as we call it, as a larger, longer line than the forward reaction. So reactants to products, we call the forward reaction. Reverse reaction is products to reactants. So with chemical equilibrium, when a reversible reaction occurs in a closed system, there's no energy or matter that can be lost or gained. So we want a situation where we're not just releasing a gas into the atmosphere, or we're not changing the environment that it's in. We want them to be able to go back and forth. The reaction will eventually reach a point where the forward and the reverse reaction occur at the same rate. We've been talking about rate in the last chapter. The forward reaction forms the products, written on the right, and the reverse reaction forms the reactants, or what's written on the left. So if we think about rate, this is a clicker question for us. When the reactants are initially placed together, how will the forward and reverse reactions relate? Look at those answers for a moment. Well, initially, if we think about it, I take a beaker or an Erlenmeyer flask and I put two liquids into it. They're going to start reacting. So initially, the forward reaction rate is going to happen very rapidly in comparison to how it will be later on down the line, because it's almost all of those reactants. So those reactants are going to be hitting one another, they're going to be forming the products. So at the very, very beginning, the reverse reaction is not occurring because there's none of the products to go back in the reverse direction to the reactants. So D is the correct answer here. If we take a look, we can sometimes draw our rates this way and figure out where the equilibrium is. So as I go with time in seconds on the x-axis, concentration in moles over liters in the y-axis, the point where they reach equilibrium is where the lines start evening out, when the rate is not changing. So the point where the reaction has reached equilibrium is where the relative concentration and rates remain the same. And it might be exactly the same, like we see in the bottom graph, or it might be at different concentrations, but we see that the rate is the same. We're not having a decreasing and an increasing rate anymore. We have one straight line. That's where we know we've reached equilibrium. So let's look at this. When dinitrogen tetroxide liquid is placed into a heated closed system, it will vaporize, then decompose into nitrogen dioxide. Conversely, the nitrogen dioxide will dimerize, that means it's going to take two and go together to form dinitrogen tetroxide. So the balanced reaction, first of all, dinitrogen tetroxide, that's N2O4, goes to NO2. Well, we know that if we balance that out, we have 1 mole of the N2O4 and 2 moles of the NO2 to get the reactants to balance the products. What happens when the concentration of dinitrogen tetroxide as time passes? Well, we know that it's going to start decomposing into that nitrogen dioxide. So the concentration of it is going to decrease rapidly at first and then more slowly as it plateaus, because we know it's going to get that time where the rate is not changing. So C is the correct answer. And why does this have to occur in a closed system? It's because if we are vaporizing it, we're turning it into a gas. If I let the gas go into the atmosphere around me, it's going to get far, far away from one another. The gases are going to disperse as much as possible, and so they're not going to be able to hit one another as likely and form that dinitrogen tetroxide.